All right, folks, and we are recording a new screencast here for a different version of the virtual geology or virtual earthquake lab. I originally used this lab for years. Then it was updated, as I started telling the folks in front of me here. It was updated a few years back to the one that shows up on your README first here. But things it doesn't always work consistently and reliably for people. We get a lot of JavaScript errors and stuff like that, and that's not cool when you guys are just trying to do a lab for me. So we're going to go back to Old Reliable here, Old Faithful, and hopefully it will work out. I've got about 14 minutes to talk about this till my timer runs out, so I'm going to try to make it all the way through the lab. We'll see. We might have to reboot a few times. What you're going to be doing is picking at the bottom of this page here one of 4 earthquakes. We're going to do one in class today, and you guys are then going to go out into the world and pick one of the other 3 to do for your homework, for your assignment. And it uses a lot of the terminology that we've talked about already and some that is going to come, but it does a good job of explaining that untalked about material to you, so I'm not too worried about you going out there with only half a lesson in earthquakes. You're going to be looking at actual data from real earthquakes. You're going to be plotting using that data, triangulating, and finding an earthquake. So let's just get started. And I'll ask you guys out here in front of me now. We got 4 choices here: San Francisco, Southern Cal, Japan, or Mexico. You guys pick an earthquake for us.
San Francisco.
All right. Now that automatically removes San Francisco from your list of homework potentials, okay? And same thing for you folks at home. All right, San Francisco it is. All right, there's a map of the region, and these are not only cities here, but these are areas where there are seismograph stations set up, okay? We talked about S waves and P waves already in class, and we told you that various characteristics about them. Primary and secondary. Call them primary waves because they arrive at the seismograph first. That's the first hit that the pen makes. For those of you at home, I just did that wiggly thing that my hand does. We've all seen in some movie or another when there's supposed to be an earthquake, of course, or maybe some giant monster shaking the ground, that these scrolling pieces of paper with the pen on them, and it bounces up and down and makes a record of those sound waves coming through. The implication to you guys is, and rightly so, that the bigger the wave, the stronger it is. That is actually true. I clicked a little too early. So what we need to do is, the first set of instructions is right here at the bottom. You need to measure the time lag between the arrival of the P wave and the S wave, okay? And the P wave is the first set of waves to hit. Usually they're not the biggest. Then we need the S wave, the second wave to hit, usually hits a lot bigger. And it's not exacting, but you need to be as accurate as you can be. These little blue lines are really tough on the eyes, especially my old eyes. But they've done you one nice favor, and they've recalibrated these to all start at 0. That's one thing they tinkered with, okay? So instead of this being some arbitrary time when the earthquake actually hit, they've dropped to 0 where the P wave hits. So all you really then have to do is go over here to where the S wave hits, drop down, and decide the value. I'm going to say that we're looking at 49 for this one. It's arguably 50, but we're going to say 49 just for the hell of it here. All right. P wave hits all the way over here for the S wave. Here's 70. We'll call that 72. If you guys strongly disagree with me, feel free to argue. 60, 62, 64. So, again, you're calculating the lag time between the S and P waves hitting. And as you can see, there's quite a variance in time here. We may ask you to prognosticate something. I don't know where I was going with the pro there. Why we see variances in lag time. a little later. So let's hit convert. All right, now we've got the time travel tables. Okay, technically they're travel timetables, but I like time travel tables better. You guys read this stuff when you're actually doing the lab. Okay, I'm kind of talking through it. I'm paraphrasing what's in here. There's a number of different waves that we could look at. The arrival of the P, the arrival of the S, or that SP lag that we talked about already. And that's indeed what we're going to keep. So they only keep one of those three lines for you here. And what you're basically going to be doing is looking at the lag on the time thing here. And our first one, for instance, we picked 49 seconds. So we go up to 49. We go across to the curve that they want us to hit. And then we'll go straight down. And that should tell us an epicentral distance. In other words, how far away the earthquake occurred. So 49 hits right here. How are these divided there, you folks in front of me? We got 400 to 500, and then we got 1, 2, 3, 4 lines in between. What increments do we got? 410, 420, 430, 440. Does that work? No, it doesn't. Yeah, 420, 440, 460, 480. So we're looking at 480 here. And again, they may have skewed these a little bit, so they always end up on nice lines for you. But I'm led to believe this is very close to real data. Up here to 72. These are by ones, so we want to go up 2 blue lines. And again, this is kind of hard to do. Keep an eye on this as you're moving your mousey across. And we go straight down to 700. And lastly, 64 seconds. Getting a little sloppy here, trying to speed up. 620. Look good? Looks good. Except it's in kilometers and we're in America, but we won't complain about that. Excellent work, you guys. The illustration to the right shows a map of the earthquake region. Here's something I neglected to tell you, but it's a perfect time to tell you now. When a seismograph receives a signal, okay, a hit, it's really easy to calculate how far away it came from. We just did it real quick, okay? What it doesn't tell you is what direction it came from, and that's why we have to do this. All it tells you is a radius. 300 miles in any direction we hit a wave from. This process is called triangulation. You use 3 points to find a fourth. It's done quite frequently. It used to be done with GPSs and even cell phones. I think that the technology's caught up a little bit, but don't quote me on that. They may still use triangulation off of cell phone towers and stuff like that. The idea being that with these varying radiuses, all 3 circles should cross in 1 point. And depending on how poorly you measure, will depend on whether 2 of them line up, 3 of them line up, or sometimes even none of them. In this point, in this case, we've got a point right about there. All right. And I think, as it already did congratulate us, so we must have done fairly decent. So we located it. Now we're going to go back to those same seismograms, piece of paper that comes out of the seismograph. And again, please read about magnitude. I've already explained to you roughly it is the height or the amplitude of the of each little peak that we're going to look at. But do read about it yourself. Remember, I'm on a time limit here. And there's yet another scale bar that they're going to use. Okay, all these scientists have set up all kind of neat doodads. All right. So, which one was the S wave? The first one or the second one? Second. Great. All right. So we want to find the maximum height here. And you don't want to pick just the first hit. You really do want to find the highest one. And how are these divided? Looks like tens. 50, 60, 70, 80. I can't tell if it goes all the way up to there or not. We're going to call this 285. We might be wrong on that one. As the semesters move on, my eyesight gets worse. 60 for this one. And lastly, 100. So we've measured, and we're going to take it onto the nomogram. And again, the idea between triangulation, that 3 points should meet. We have an approximation right here. It looks like what do we got? There's 7.5, so these must be increments of 1. So I'm going to call that a 7.1. See how it's crossing right at the first hasher mark there. 7.1. Hey, congratulations again, you guys. Seismograms of the earthquake you chose to study have been modeled after a strong trembler that occurred in 1989 south of San Francisco. The Loma Prieta earthquake took place during major population centers, caused significant loss of life and property. Estimated magnitude was 7.1. Your magnitude of 7.1 compares very well to that estimated by seismologists. So we did as good a job as professional seismologists, huh? You know, we'll see. We had a lot of hand-holding there. So we will call this Earth Science class fall 2016 MVCC, Utica, New York. Do not attempt to email this to me. You can fill this stuff out. 30% of the time I actually get it. All right? I'm going to show you instead what you're going to send to me. You're going to go down here and hit Get Certificate. Before we look at the certificate, we're going to look at our numbers. So, SP interval 49, 49, 72. Ooh, I'm good. Especially for my elderly eyes. 480, 478. Oh, well. 700, 703, 620, 623. The exception of this, even, you know what, the 480 to 478, that's not too bad. Here's the one I was worried about. 285 is actually 277. I don't know about that. 60 to 57, 198. Again, these are a function of these, so it compounds. If you make an error, it does compound. But in the end, we were close enough, apparently, that we got the actual magnitude. So what you'll send to me is a copy of this. Now, I'm on a Mac. I just drag it over to here. You guys with PCs, you could probably right mouse click. Another thing to do, of course, and I don't know if I could take a screenshot while I'm doing a screen capture, but we'll see. It made the noise. You can make a screenshot, and lo and behold, it's there. You'll want to do a quick trim. Boom. Again, I've got a Mac, so this is horribly easy and simple. No, I'm sorry, I'm an Apple tool. You knew that, though. All right. This is what you email me, okay? This is what you guys email me. I'm going to print out a copy here. Feel free to put one of these on your fridge at home. You might need it over Thanksgiving, okay? Your folks are hassling you about not being a good student maybe or something like that. Whip out your virtual seismologist certificate and show them that you are very good at finding earthquakes, okay? All right, so I'm going to wind up this video. If you have any additional questions or concerns, please feel free to email me. As always, you guys know that. This is due in 1 week. Even though you don't have lab next week, do it so you don't forget.